So last time we considered such electric circuit. We had a battery. Okay. Battery plus minus capacitor and load resistor. So here was a switch and position A and position B. So our capacitor C, resistor R, and electromotive force epsilon. So initial case which we considered was putting the switcher in the position A and start to charge the capacitor. So we can probably tell something about the processes which are happening. So we discussed that definitely we have some current flowing through this circuit, but that is very short-term current, which is not constant in magnitude. So why it is not constant in magnitude? Why we don't have uh, constant in magnitude electric current in this circuit? We discussed this last time. Any suggestions? Because we charge the capacitor. Yeah, so we can claim that here is open circuit. This is the electric. We cannot have a steady electric current flowing through this circuit, but there is an option to accumulate certain charge at this capacitor, and until this charge will be accumulated to that point, there will be some current flowing through this circuit. What will be the maximum charge which can be accumulated at this capacitor? Or in other words, what will be the highest potential difference between these two plates of the capacitor? So since we don't have any current, when this capacitor is fully charged, means potential difference at the terminals of this capacitor or at the plates of the capacitor should be equal to electromotive force of the battery. So they have opposite polarities, they compensate each other, and there is no conditions for any further charging processes of the capacitor, and that means there will be no current. So we derive some expressions for calculating the time dependence of electric current in this circuit. When we go from t equals 0, assuming that there is no charge accumulated at the capacitor. So what did we use? First of all, we have to apply second Kirchhoff's law. And from there, we express electric current as a function of parameters of the circuit. Consider that electric current is the first derivative of charge over time. And then we have simple differential equation with separable variables, which allows us to get the expression for charge accumulated at this capacitor as a function of time. What do we do next with this in order to get current? We take the derivative. So current is first derivative of electric charge over change of that is rate of changing of electric charge per time. So first derivative of charge over speed, we have a function which quantitatively describes charge as a function of time. We can get electric current taking first derivative of this charge versus time. So with that, we got also expression for current dependence on time. Who will tell me what function defines the time dependence of current in this electric circuit? Exponential function. So that is very strong function which tells us that rapidly electric current will go from its maximum value. And what is maximum value? What will be the maximum value of electric current at t equals 0 for this electric circuit?
Electromotive force divided by resistance.
Exactly. So there are two factors which will define this. This is electromotive force and load resistance. At t equals 0, we don't have any charge, don't have any potential difference, so it will not have any impact on electric current. So there is another parameter which is important, and that is RC product of capacitance and resistance. How do we call it? Some characteristic time for RC chain and what it defines. What is the physical meaning of this characteristic time? So let us consider first capacitor and resistor. Assume that, for instance, we will call it quantitatively describe discharge of capacitor, but now we can just imagine the process. We have electrically charged capacitor, we connect it to some load resistor, and there will be some current because capacitor will be discharged. What will limit this current? So the magnitude of the resistance. Now the question is, let's say we have a fixed capacitor with given potential difference between plates and change magnitude of the load resistor. We go from small load resistor to large load resistor. Will it change the time which it takes for the capacitor to be discharged? So we have fixed amount of electric charge accumulated in the capacitor and two different resistors. Let's say 100 ohm and 1 kilo ohm. For which resistor attached to the capacitor, it will take longer for the capacitor to be discharged.
With the high resistance?
With the high resistance, it will take longer to discharge the capacitor. Why? What will load resistor limit? The current which flows through the circuit. Means smaller current, and that will correspond to longer time which it takes to discharge the fixed amount of electric charge. So the product of capacitance and resistance defines this characteristic time unique for a given combination of capacitor and resistor, which tells us how fast electric charge will be gone from the capacitor via this load resistor. So the physical meaning comes from that equation which we derive, and it tells us that in the time interval of this RC product, the magnitude of electric current flowing through the electric circuit will decrease in E times. So it means that it will be 2.7 18 times smaller than the maximum value at the t equals 0. So that's the definition of this characteristic time, which is a characteristic parameter of RC electric circuit. So now we consider different case. So our capacitor is charged, so we disconnected it from position A and turned the switch to position B. So in this case, we can neglect with the presence of the battery in this circuit, so we can actually even delete it here. So what we have only charged capacitor and load resistor attached to it. The same situation which we have just discussed. And now we want to know how to calculate the time dependence of electric current, charge, and so on. And we will also introduce time dependence of electric energy, electric field energy accumulated in the capacitor, and time dependence of electric power dissipated over the load resistor. So all these parameters will be considered for this given case. So we remember last time we wrote this second equation. We wrote this equation as a result of second Kirchhoff's law for previous electric circuit. So how it will change now? We just eliminate this electromotive force because we don't consider it anymore. So in this case, we will have minus Q over C minus I times R, and that is equal to 0. So we remember that electric current I is equal to dq over dt, first derivative of electric charge, as a function of time. And we can write the following. So it will be dq over dt minus r times dq over dt, and that is equal to q over c. So recall q is the electric charge which is in given moment of time accumulated at the plates of the capacitor. And the first derivative of charge over time gives us instantaneous value of electric current flowing in this circuit. So now we also separate variables. So we will get dq over q equals to 1 minus 1 over rc dt. And in order to get our time dependence of electric charge at the accumulated at the plates of the capacitor, we need to integrate this equation like left and right side of this equation. So can write it here. RC can be taken out from the integral since these are constant parameters. Here we have natural logarithm of electric charge is equal to minus T over RC and plus some constant B. Obviously, in order to get the final expression, we need to determine this constant of integration. And which boundary condition we are using now? At t equals 0, what do we have in terms of electric charge? we have maximum electric charge. Let's say this capital Q. So this Q small is equal to capital Q. That is maximum electric charge, which can be like was accumulated at this capacitor during previous example when we had our switcher in position A. So now we can take this into account. So it will be natural logarithm of Q over capital Q equals to minus T over RC. So we get rid of this natural logarithm. It will be Q as a function of time equal to maximum electric charge accumulated times exponent minus T over RC. So this is the expression for time dependence of electric charge at the place of this capacitor as it is discharged over like through this load resistor. So we see that it exponentially increases, and again here we deal with this RC product, which is the characteristic time of the RC circuit. So that defines how fast this process of discharge will happen. So how do we define potential difference at the plates of the capacitor if we know charge accumulated at the capacitor and capacitance? Q divided by C. So that will be standing for maximum potential difference at the, let's call it V naught. Maximum potential difference at the, like between the plates of the capacitor at T equals 0, because that will correspond to this maximum electric charge Q capital. So that's why we can write that potential difference as a function of time between the plates of the capacitor is given as Q over C times exponent minus T over RC, or that is equal to V naught exponent minus T over RC. So now we have another equation which provides information on potential difference at the plates of the capacitor, which is in the process of discharging via a given load resistor R. And our next step is to express equation for electric current. So how we do that? We consider this function, charge as a function of time, and take first derivative over time. So electric current as a function of time is equal to dq over dt. That is equal to, if we express it in terms of maximum electric current, it will be minus q over rc times exponent minus t over rc. So here we have this minus. So what does it tell us? Suggestions? Well, the fact that current is decreasing is shown here. So this minus in the argument of the exponent function that tells that current is decreasing. This sign minus, because if you recall from our previous discussion, there was no minus in the expression for electric current. This minus means that capacitor is discharging. So previously it was charging capacitor, now it's discharging. So this current results in the decrease of the charge accumulated at the plates of the capacitor. So now let us recall what will be potential energy of electric field accumulated inside a capacitor. We discussed this several lectures ago, and that was potential energy as a function of time. That's determined by amount of electric charge. There were different options to write it, but one of the options, that's electric charge accumulated at the plates of the capacitor divided by 2 times C, capacitance of this capacitor. So now we know how Q depends on time. So we can write here that Q is a function of time. So let us substitute here the expression for Q. So that is this function. It will be Q squared over 2 times C and times exponent minus T over RC. So this is another important equation which tells us the dependence of potential energy of electric field accumulated inside a capacitor over time as this capacitor is discharged via resistor R. Yes?
What about the score of the exponential?
Yes, you are right. So we put 2 here. Yes. Good. So that is the equation for potential energy, and you're right, this should be 2 in the argument of the exponent function. So now let us consider what is the power which is dissipated over load resistor. So how do we write power as a function of current and resistance? Is I square times R. So now we know that both, obviously, current is a function of time, and this power will be also as a function of time. So we can talk about instantaneous value of this power, which is electric power dissipated over load resistor, because current is a function of time. So now let us consider the maximum power, like not the total, not maximum, total power, which will dissipate over load resistor during discharge of this capacitor from maximum charge to 0. Means we can consider from 0 moment of time to some infinity. So we can write that total energy, because if we consider power over some time interval, that will be energy. Total energy dissipated over this load resistor will give us the integral from 0 to infinity I square times R dt. So we just consider this time-dependent function, means powers, dissipating power over resistor, and integrate it from 0 to infinity. Obviously, if we have infinitely long time interval, this capacitor will have enough time to discharge to 0 in any way. So what is your expectation before we start to run this calculation? What it should be equal to? Can we make some prediction here? So far, we didn't consider that there are some energy losses in the system, and what it means that all energy accumulated, like potential energy of electric field accumulated in the capacitor, while is discharged completely via some resistor R, should be transformed into energy which is dissipated over this load resistor. So when we integrate this power of dissipating electric energy over load resistor over infinitely infinitely long time interval, we should get the maximum potential energy accumulated in the capacitor. And that should be like capital Q square over 2C. So let's see actually what we get. So this will be integral from 0 to infinity. Here we substitute expression for our current, so this equation. So it will be minus Q over RC times exponent minus T over RC. This is in second power, and times load resistance R dt. So we can factor out this R from the integral because it's a constant. So that will be 1 over R. Then what do we have next? We have Q, capital Q square, over sorry, it's not 1 over R, it's just R, and times Q second power over R square C square. And then we have integral from 0 to infinity exponent minus T over RC dt. So we can cancel this second power and this R. And now we need to integrate it, but again, I missed the 2 in the argument of the exponent, full current. No. No. You are right. Minus T, that's correct. I missed 2 here because of this factor second power. Okay, now we have this. Now we need to make the same expression next to the differential in order to integrate this expression. So that will be equal to epsilon square, which we substitute here. So Q over C, that is electromotive force. That's the maximum potential difference at the plates of the capacitor. So keep that in mind. Then we have here resistor. And this is our integral, Q over integral from 0 to infinity, exponent minus 2 times t over RC, and here we have dt. So now we integrate this. That will be epsilon square over R, resistance, which is connected to our capacitor. Then we need to multiply it by minus RC over 2. So we do this because we have this coefficient in front of t here in the argument of exponent. And we have exponent minus 2 times t over RC from 0 to infinity. So that will be equal to 0, because if we consider infinity instead of t, and with this minus, exponent will give us 0, minus epsilon square over r times RC over 2. Because when we substitute 0, we get just unity for exponent. So that will be, here r is cancelled out, and we get c times epsilon square over 2. So that is the amount of energy dissipated over resistor during discharge of the capacitor from initial stage when we had this potential difference between the plates of the capacitor equal to the electromotive force of the battery. So now let us write down the expression for potential energy, so the maximum potential energy which was accumulated in the capacitor. So that is given by this equation, but we need to substitute capital Q, the maximum current accumulated. So that is Q square over 2C. And here we have expression for total energy dissipated in like over a load resistor, and that will be C times epsilon square over 2. So technically this is the same expression, because we can write here that this is Q square divided by 2C. So the product of capacitance and electromotive force gives us charge. So if we consider Q, capital Q, in second power, like here, we need to divide this expression by C in the denominator. So these are the same magnitudes. We indeed will dissipate over resistor the same amount of energy as was initially accumulated in the form of potential energy of electric field between the plates of the capacitor inside this capacitor at t equals 0. So let us summarize this discussion. And once we have already charged capacitor, which was charged after considering the first part of this story when we connected it to the battery. So we charged it, then we switched the position to B, So we disconnected the battery. We have charge capacitor and attached to this capacitor load resistor. We let this capacitor to discharge via the load resistor. This load resistor will definitely define the magnitude of electric current. And this discharge process will be also defined by the exponential function, which has a characteristic parameter, RC product, this tau. So the larger load resistor, the slower will happen this discharge process. In any way, this time dependence of electric current will be exponential, so it will exponentially decay, and so will do the electric charge accumulated at the plates of the capacitor, potential difference between the plates of the capacitor, and also during this discussion we considered how potential energy of accumulated electric field inside the capacitor will decrease over time as it discharges over load resistor. And we figure out that indeed it will be equal to the energy dissipated over load resistor as we let this capacitor to be fully discharged via load resistor from like within the interval of time from 0 to infinity. So why it happens? Because we consider zero energy loss in the process. So we any suggestions where, for instance, could be some energy losses in the circuit. If we assume that this electric circuit, RC circuit, would be not ideal. Hmm? Heating of what? Because we consider heating like Joule length heat dissipated over load resistor, but we have also connecting wires. So that's one factor which could be taken into account if resistance of these connecting wires are not small enough, they are like not negligible in comparison to low resistor, then we might consider heat dissipation over these wires, and then the power, the total energy dissipated over load resistor will be smaller than the potential energy of the accumulated electric field in the capacitor. And another option which could be considered, keep in mind that ideal dielectrics do not exist, and even so we consider that resistance of the capacitor is equal to infinity. Indeed, we have some leakage of this accumulated charge at the plates via the insulator, and if we keep for a long time between these moments of switching from position A to when we detach the capacitor from battery, so let this capacitor stay in charge position, and it takes some time to switch it to position B, there could be some leakage of this electric charge through the insulator of the capacitor. That's why we will lose it. So we will lose part of the initially accumulated potential energy inside the capacitor. And eventually, when we measure total energy dissipated over the load resistor, it will be smaller than we assume was accumulated initially in the capacitor. So those factors may be taken into account, but not in this given example. So here, this potential energy is equal to energy dissipated over resistor. Thank you very much for attention. We will continue next time on Monday with introduction of magnetic field. And have a good weekend. See you on Monday.